Hello friends, today we will study what is binary search. But before coming to what is binary search, let us see or let us find out why do we need a search algorithm. Searching is any time needed when I need to search a data either on my laptop or on my computer, that is if I am searching for any file or if you are searching for any contact in your phone book. Search is always been necessary to find a relevant data whatever is needed by the user. There are two searching approaches which are used. One is a linear search and a binary search. Linear search uses a simple strategy of finding the data by comparing each and every element to every element in the list. And if my list is very large, then it becomes very tedious to check every element with every single element to what I am trying to search for. So it increases the time complexity of my algorithm. So comes into picture the divide and conquer technique which is applied in the binary search technique. Let's see how this binary search works. Binary search works on a sorted array list. This is the first and the foremost criteria to implement a binary search. Binary, as it means, it can be either 0 or 1. So binary is applied to a strategy that I have to always have a sorted list. When I use this divide and conquer technique to search an element in my list, I sort the data. Now, for sorting the data in my list, I can use any regular sorting algorithm to sort the particular list. Either I can have a bubble sort or the normal quick sort if you want the data to be sorted faster, but then it increases some complexity of my program. So we usually sort the elements using the bubble sort technique, which is the simplest method to sort a particular element in a list. After sorting, what we do is that if the list is sorted, see the first step and the foremost I have said that if the list is not sorted, then the first step before performing the binary search is to sort the array using any sorting technique. And then what do? Binary search is the fast search algorithm with a runtime complexity of O log n, that is the big O log n. And then binary search will look for a particular item by comparing the middlemost item of the collection. So in the binary search technique, I find out the middle element in the list and then I compare the element I need to be searched whether it is present in the middle or not, and then recursively I keep on finding the middle and then search whether my element is present or not. And if the match occurs in the middle, then the index of that particular item is returned. That is, if my element is found in the middle, then I return the middle index of my array list and I say element is found at this particular position. And if whatever element I am trying to search is greater than the item, then the item to be searched is searched in the right side of the subarray of the list. If the element I am searching is less than the middle element, then I search on the left side of the subarray. So with this, we get a very clear picture that what is binary search. I find the middle of the array, and once I get the middle position of the array, I check whether the element is present in the middle. If not, I find out whether the element has the value less or greater than the middle array. So here also, using the divide and conquer technique, we've partitioned my list into two parts after finding the middle. As my array list is sorted, So there is no confusion that the element is less or greater will be present in the left side or in the right side of my subarray. The process continues on the subarray until the size of the subarray reduces to 0. This is one criteria, till the subarray reduces to 0, or the process will continue till I have searched the particular element in my list. Once the array is complete and my item is found, then we say the element is searched using binary search. Now, we've seen what actually the binary search do. Now we'll see a pseudocode for the binary search algorithm. Now, this is a procedure which is named binary search. What happens? It says A is a sorted array, N is the size of my array, and X is the value to be searched. So, the basic three requirements is, once I have an input array, I am presuming that the array that we have entered is sorted. So, we say the input is a sorted array list. N size and X is the value to be searched. We set the low value to be 1, that is the beginning of my array is set to 1, and set high is equal to N. N is the last element of my array. And then while X is not found, we say, and we enter the loop till I have not found the value of X, and if high is less than low, then only we say if high is less than low, that is if N is less than 1, if N is 5 less than 1? No, 5 is greater than 1, and if at any position my high becomes less than 1 and the element is not found, we say X does not exist, that is the element is not found in my list. If the element is not found and we say the element exists, that is the value of high is greater than the value of low, then what we do? We find the middle element for that particular list. So we say mid is equal to low plus high minus low by 2. So this is how we get the value of mid. In this case, we have set the value of low as 1, the value of N if we consider is as 5, then it will be 1 plus 5 minus 1, 4 by 2. So my mid will be 1 plus 2 is equal to 3. So for my array list 1, 2, 3, 4, 5, if these are the index values of my array, then my mid is at a position 3. So whatever element I am trying to search, I will try to find it at a position 3. We found that if we search for the middle element, and we've seen the middle comes with low plus high minus low by 2. Now we see if the element is found at the mid, and if it is not found at the mid, what do we do next? We search if my A of mid is less than X. So what happens is, if yes, then what do? I say low is equal to mid plus 1, that is it is now found in the upper bound, that is the value of X that I need to search is positioned or is present on the upper side of my array, that is the left side of my sub array. So my low becomes mid plus 1. The example that we've seen, or the example that I had shown, that 1, 2, 3, 4, 5, my 3 is mid, and if the element to be searched is on the upper side, so mid plus 1, so my low becomes now 4. So we've seen that if the element to be searched is to be found on the upper bound, then low is equal to mid plus 1, and if the element to be found is less than mid, that is my mid is greater than the element to be searched, then I say high is equal to mid minus 1. So here my high becomes mid minus 1, my mid was 3, my mid was 3, so 3 minus 1 is 2, so high becomes 2. So we see that the values of low and high will be varying depending on the element which is to be searched, whether it is greater than mid or it is less than mid. This is an approach of a binary search which divides my list into two parts after finding the middle element of the list. And if the element is found in the middle, then we see element is found at a particular location. So this function will work recursively to search a particular element in a list. And with this we end the while loop. Now this will work recursively in a continuation, and here the procedure comes to an end. Now let's see an example of what happens. Here I have given is the index location of my array. If you see, it goes from 0 to 9. As it specifies it very clearly that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are my index locations, and 0 stands for low and 9 stands for high, and it has 10 elements in my list. This is the elements of my list. The highlighted number 35 is a number which needs to be searched for using binary search algorithm. So my list, if you see, is a sorted array. I am accepting that what is known as A as an input, which is a sorted array. So I am not applying any sorting technique on this particular array. But if the user enters a list which is unsorted, then make sure that you first sort the elements of the list, and then only you can apply the binary search algorithm. We see the list is sorted, 35 is the element to be searched. So we first find the middle of the list as given below. The formula for the middle is mid is equal to low plus high minus low by 2. Here we see that low is 0, high is 9. So we do 0 plus 9 minus 0 by 2. If you see, the answer is 4.5. So we round off to 4. So now what happens? The position 4 has element 28. So my mid is at location 4, element is 28, which is highlighted. What do we do next? For this particular thing, the sorted list, we've found the element 28 at mid and 35 is the element to be searched. So we check whether the element to be searched is present at the middle. 28 is not equal to 35. So that particular condition is not satisfied. Now what is the next condition? The next condition is I search whether my element is present on the left side of the subarray or the right side of the subarray. To find out that, we observe that 35 is greater than 28. So we search the element in the right side of the list. You see the advantage here that 28 is the middle, 35 is greater than 28. So we go to the right side. As a result, we have discarded the half of the list which is on the left hand side. So my time and the space complexity has reduced. I don't have to unnecessarily search my element on the left hand side of the list. So we've shown here in a discarded manner by scratching that the left hand side of the list is discarded and the right hand side of the list is where we're going to search the element 35. Now what happens? For this particular 35 that is on the right hand side, we do low is equal to mid plus 1. So when I say low is equal to mid plus 1, the location where 32 is stored becomes the low for my array and high remains at 9. We now recursively execute the binary search algorithm. Now here if you see, my low is 5, my high is 9. So what do? I say 5 plus 9 minus 5 by 2. 9 minus 5 is 4. So 4 by 2 is 2. 5 plus 2 is 7. So where is 7 coming? 7 will come for the location 47. Now my new mid, which is recursively found, is at 47 where my element is stored. So I will again check whether 47 is equal to 35. We say no. We observe 47 is not equal to 35. So we go to the next criteria and we check whether the element to be searched is present on the left side of the list or to the right side of the list. As 35 is less than 47, so we discard the right side of this array and we come to the left side of this subarray, and then this will recursively proceed. You will observe that in 2 iterations for the array list of the size 10 elements, we have reduced down our search to 2 elements, that is 32 and 35, rather than searching for the complete list, which is a possibility in the linear search algorithm. This implements the divide and the conquer technique, as we have divided and conquered our solution and reduced down our list to 2 elements. So what happens is we take the code for it. How does this code actually works? Initially called with low is equal to 0 and high for n minus 1 if n is taken as 10. Then if n is 10, then my low is starting with 0. So my n has to end, that is my high has to end with 9. So I have taken n minus 1. If we have put our low as 1, then our high will be n. That is how we will be implementing the binary search pseudocode. Now we call this particular function binary search, which goes from array A 0 to n minus 1. The value we passed, which is to be searched, the low and the high of my array is passed. We start. If high is less than low, then we return the low value. Mid is equal to low plus high minus low by 2. That is the normal. We finding the mid of the list, and then we keep on checking whether mid is greater than the value. Then we return the binary search and we say mid minus 1. That is, my value is less, it is on the lower side. So I recursively call this function with a binary search and we pass mid minus 1 as my high value. And if on the else part, if my mid value is higher, that is my value is higher than my mid, then what do? I do instead of low, I pass mid plus 1 and my high remains the same. We see that binary search recursively calls the binary search procedure when we change the value of either high or low, whatever is the requirement depending on the element to be searched. This recursive function continuously works till either my recursion, that is my array size, becomes 0 or I have found a particular element in the array. This can be recursively also used if I have to find out the position of the element which is needing to be searched. Then I can return the value is found at this particular location, and then we can have a count value which will keep on incrementing to tell us what is the count of the element to be searched in the array. Now seeing the pseudocode and the example implementation of how the binary search will work, now let us see what is the importance of binary search. As searching always holds a special importance in any algorithm or in any implementation, whether we are searching any key or any data on Google or any data on computer or any data in our phone book, the algorithm has to be implemented using a search key. So binary search is a programming method used to search through data to find a particular element, item or a record. So whatever we are searching for will always be searched using binary search. As we increase the complexity, binary search gets added up with many more algorithms to search a particular data of string matching and implementing and segregating the data. The data must be in order for the binary search to work. That is, I have to have my data in a sorted form to search an element in an array. It takes far less comparison than the serial searching to find an element. That I've already told that if we have to search an element using linear search, then I need n comparisons. Whereas when I have to search an element using binary search, then it takes O log n, that is, my search is reduced. We just now saw in the example that if I had to search the element 35, then in my third iteration I had reduced down to a search element to 2, where the size of my list was 10. So this is how the binary search using the divide and conquer strategy reduces the searching time and its complexity. Binary search algorithms are more complicated to write and understand than a serial search algorithm. This is one simple disadvantage, as I need to recursively call binary search. Some people even try to implement by finding the mid of the element and then applying a linear search strategy to the smaller subarrays. But that again adds up to the complexity of my binary search. So binary search is easier to implement if used recursively using the divide and conquer technique. The divide and conquer technique, as we've seen, will always divide my arrays from n to n by 2, hence and so forth. So binary search is the suitable searching technique to search any element in a large list size, so that I can reduce my time complexity and get a better search in a stipulated, or rather a reduced amount of time. Thank you.